Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
So I have a little setup here of our situation. We have a wire that we're given the total length of that is made into a square and put into a magnetic field. And it's a motor, so we have this axle running down the middle. And then this is set to rotate when it's in the magnetic field, so it rotates around the axle. Okay, so now we know the total length of this wire, and it's wrapped into a square, which means that each side of this square is 1/4 L, or L divided by 4. But because this magnetic field is parallel to two sides, we have this top side here and the bottom side are parallel to B, which means that it's not going to have any force in this direction, so it's not going to have any contribution to the torque, the total torque. Because we know that magnetic field relative to current involves a sine of phi, or theta in the forces case. There's an angle involved either way, and it has to be perpendicular to each other. If they're parallel, they don't contribute any force. So our area that we need to take into consideration, we only have two sides. So this is the hard part for this problem, is figuring out what we need to use for our area. So our equation for torque, which is what we're looking for, is number of turns times the current times the area times the magnetic field sine of phi. And we want when our torque is at its max, which means that we want our phi here to be 90 degrees, because that maximizes this equation. Every other value of phi less or other than 90 degrees, so when phi is 90 degrees, we have sine of 1, which is the highest value for sine. Every other value is going to be less than 1, which will lower the value of this total torque. So when sine is 90, or when the theta, our phi here is 90 degrees, we have our maximum we can get, which is why I've drawn B perpendicular to two sides. It can only be max for a total of being perpendicular to a total of two sides. So we could draw it up and down and reverse this axle, but this direction works fine for our maximum torque, which is perpendicular to two sides. So we have B, we have N. We actually want to calculate for 1N and 2N, which simply change it to 2 after calculating what 1N is. So we also have B. We need to find this area, though. So area is a question mark at the moment. So we have our total length, and we have that one side is 1/4 L, but we only have two sides that contribute. So that means if we take our area, which would be the inside of this square here. So typically, if all sides contributed, if this magnetic field, say, was into the page or out of the page, so if it was coming out or in, it would be perpendicular to all four sides. Our area would be equal to one side of the square squared. So this number squared. So L divided by 4, which is one side, times another side. So this would be another L over 4, because it's a square, so they're all the same length. So we times this side by this side to get our area. But we only have two sides that contribute to our overall torque, which means we need to divide that by 2. So it's the typical area cut in half. So using this number, and we also are given the current, we are able to calculate torque now using sine of 90 degrees, which is 1, so this whole part drops out, So we actually have to do this twice. We have tau. The first case, n is equal to 1, so we don't need to take that into consideration. We have the current times our area, which is this. So you take your L, divide it by 4, square that, and then divide that number by 2. That's your area and the magnetic field. And then for part 2, for 2 coils, that just means we plug in a 2 for n instead of 1. So this you take what you get for part 1 for 1 coil and just multiply that by 2 for 2n, and that'll give you what 2 loops would give you for torque. And there you have it.